Happy Chinese New Year! 新春快乐！恭喜发财！恭喜发财！ And 迎春接福 This means welcome the spring and embrace the fortune. Thank you guys for coming. Today, I'm gonna give you a very high-level overview of the BERT paper, which was published 2.5 years ago, but I think it still has a solid importance of reintroduce the paper. So once you are watching my paper reading sessions, you get better understanding of the fundamentals and get to know the papers better. Okay, first of all, I think I'm gonna give you a very quick overview of the thing called transformer. Okay. Transformer. I do have a paper reading session in our channel. Feel free to search the keyword transformer in the channel so you can find a more detailed version of the transformer paper reading. And the fundamental part of the transformer is this. So there is an encoder which takes input. For here, I would just use the textual input, for example. For instance, the input is I am Wei. Okay. And therefore, after the encoder, you got some sort of embeddings. And the embeddings will be passed into the subsequent what? Yeah, you're right. To the subsequent decoder. And decoder will generate the output. For instance, suppose the transformer is doing the machine translation, and it's supposed to be translate into Chinese. Then you will see the Chinese character here. 我是伟, right? And usually the decoder, especially in the speech recognition case, I don't know too much about the NLP case. For the speech case, they will have a loop back into here. So the input is like yi minus 1 and the output is yi. Okay. And the key contribution of the authors of the transformer, I think, is the propose of the fairly efficient algorithm called self-attention, which significantly accelerated the training or the GPU training. Okay, we can find all of this in here. Okay, and remember this, the transformer here is a supervised learning. What is supervised learning? Supervised learning needs to have two key components. The first is input. The second one is you have to have the output during training or transcribed output. But once in the BERT paper, it's not a supervised learning method anymore. It's called an unsupervised learning. So you can tell the meaning literally from the word unsupervised. Nobody is watching you, and nobody is giving you suggestion, advice, or direction to go. So basically the BERT, if you take this BERT as like a black box, and the input in the NLP case would be sentences. For example, I'm Wei, he is Jim, etc. Right? And what is output? Because you don't have any transcribed output, so the output would be something called embeddings. So you may ask, wait, what is embeddings? Embeddings in the domain of matrix or math, it's like a vector, okay? It's like a feature vector. Say, for the I am Wei case, each word or each word piece would, after it passed through the BERT, you will get a one-dimensional vector, and the vector represents the word piece, how the word piece is being mapped into some vector in the feature space. And then once you have a full sentence, I'm Wei, for example, then this feature vector would be expanded to a matrix. A vector would go to a matrix, right? And then this is the number of inputs. And this is the embedding dimensions. Okay? And suppose you're doing this in deep learning style thing, and you're doing this in a batch mode, right? Sorry, not batch mode, in a mini batch. So you can have a three-dimensional array or 3D matrix. Sorry about my drawings, but I try to get everything good. So what is this? So this is your batch size. Okay. And then now let me go into the details on about how this black box would be look like. Before I start, I would like to give you, and I would say, I do not want to go over the details of each layers, layer norm, batch norm, these type of things, but I would rather give you the high level structure of the networks, especially the key new ideas, especially the key ideas that is being introduced into the BERT architecture, which is called MLM. So I think people are talking about this MLM in the past 2 years many times, but what does it mean? It means masked language model. Or mask LM. Yeah, they are the same thing. So let's take a look at the pre-training one on the left. Let's see if I can zoom in a little bit. So you can see, so the input, I can have input, right? So in the NLP case, suppose I have two sentences. Example, I am Wei, and this is a sentence separator, and he is Jim. So before I got the input into the BERT input, the author need a something called a sentence piece module, which will convert the textual input into the word pieces. This is like a word sequence, right? And this would be a word piece sequence. Let me ask, what is a word piece sequence? The basic concept is that to reduce the size or dimension of the input space. Because what? Think about some chemistry word. Sorry, I'm not in the chemistry domain. I cannot name one. So it's like something like recently, like a carbon dioxide. Carbon dioxide. It's one word, but you definitely can regard this thing first as carbon or dioxide. Even the dioxide can be decomposed or into two parts because the di represents means two, right? Oxide means oxygen or something. Yeah, so you can either decompose the word into carbon dioxide or carbon di and oxide. Here, so you can see even the English word dictionary can easily have more than a million words. But in terms of the word piece, you can definitely constrain the size of your word piece numbers down to about 1,000, or in fact 1,000 is a little bit small, maybe like 1,000 to 10,000 level. So this will limit your input features dimension. So this one, you got word piece, right? I mean, this is maybe my way will become decomposed like to this, right? The still space. He is, maybe Jim is gonna be decomposed into this, right? And then you pass this through the transformers encoder. And don't forget this. Encoder uses self-attention, so it would take all the input at once, right? So the encoder would have a way of assemble all the inputs together and have the possibility of calculating something called either something like a correlation between the words in the inputs or the word piece in the inputs, or say it's the self-attention. Okay. And after the encoder, definitely the encoder, the author said their difference compared to OpenGPT is that they do bidirectional encoder. OpenGPT only does a unidirectional. But I think it's trivial to me because I think the biggest contribution is the MLM, which I will cover very soon. Okay, OpenGPT is this. BERT is this. You may say, okay, in the transformer, after you pass this through the encoder, you got something called embedding, right? Embeddings. And then this is going to be input into something called a decoder. So you have the output, right? So what are you gonna do here? So what people are doing here is fairly simple. Although they don't have the transcribed output like the supervised transformer, they're doing this. I think what they did was they offered a very simple decoder. I'm sorry I didn't look into the details of the decoder that is being used during the BERT pre-training, but I assume it's a very simple decoder because you want to learn all the input correlation things into this encoder, not the decoder. So you want the decoder to be as big as possible, but the decoder to be as small as possible. And what is the output this time should be? So the output is still these word pieces again. Still I am way space is GM. Then you ask, okay, wouldn't this be too simple for the deep neural networks to learn? I said, you're right, because the network would just say, okay, whatever is input, I will just give it to the output, and whatever and for the next layer, whatever the input is, I will get passed to the output, and the ReLU layer, you just do the activation of one input and one output. Nothing got learned here except you just learn it. You give me the input, I give you the output, and here is the smart thing plugged in, MLM. Dr. Jacob, he said, what we should do is we should randomly mask or take certain words away from the input sequence, but you keep a null or blank mask symbol over there to occupy the location, okay, in the sentence. So after masking this, can the encoder plus the simple decoder be able to recover the original word piece input sequence? So this time get tricky. So it's like a guessing game, right? So the encoder would say, okay, what I'm gonna do is, because this time I do have a target, during the pre-training, although it's not transcribed, I do have the original sentence that's being input. I know the target is. And my decoder says, okay, how can I leverage the words or the word pieces next to the word that is being masked to see whether I can recover it. So you can see by doing this type of loss, you're forcing or enforcing or push the encoder to learn the correlation information between the words. And in this case, Dr. Jacob used the sentence pair example. This is sentence A, and this is sentence B. So even I think, in my opinion, it's capable of learning the two grouped inputs correlation or attention things. So you can see, you can learn the correlation from here to here and here to there. And you may ask, why it needs two sentences? Can I just do one sentence? I think it's fine. You can do one sentence, two sentences, or even one paragraph. As long as your GPU memory is large enough, it can hold the input, because you see the encoder takes all the inputs in it, and calculate the self-attention between all the words in the input. So it got to take lots of memory. Okay, like we mentioned, after they do the MLM, learn the embeddings, here is the interesting thing that's going on here. Let me wipe out this, I don't need this. So after they train the pre-trained model or embeddings, they are applying this embedding down to different downstreaming tasks. For example, this is the decoder 1. What is decoder 1 for? It's called squad. Right? Squad. Squad is like a QA task in the NLP, question and answer task. And this embedding can also be used for another downstreaming task called NER. NER is name entity recognition. For instance, you want to recognize the entity names in the sentences, okay, and etc. And in this case, let me ask you this. Is this a fine-tuning thing unsupervised or supervised? You can pause the video and think about 10 seconds. Okay, the answer is the fine-tuning is and always supervised. And it's a downstreaming task. With annotations. And you can see during the fine-tuning, it's exactly the transformer model, right? You can see you have the input, and you have the encoder, and you have the decoder, and you have the labeled or annotated outputs. Although the outputs can be different, for example, the NER could be 001, 000, something like this. 1 means the net entity, and squad means whether the question and answer makes sense or not. So all in different forms, but you can see the architecture now here uses the transformer architecture. Okay, so now let's move on to our the last part of our audio, which is the third part. What's the connection between the BERT and speech-related applications or techniques? For instance, automatic speech recognition, speaker ID, language ID, emotional recognition. Many things. First of all, let me ask you, can BERT be easily applied to the speech task? You can pause the video for 10 seconds and think about the question and resume. Okay, the answer is no. Why? Because originally the BERT is designed for NLP tasks. So even for NLP tasks, even NLP or the text in NLP doesn't have an annotation, for example. It doesn't have the annotation of name entity. It doesn't have whether the question and the answer pair makes sense or not. But it always in a structured form. So structured form. structured form, I think. Structured form. So it will all be in a word, word 1, word 2, and word n. And the word, as you see that, it can be easily be decomposed into word pieces. Word pieces. And then, like I just mentioned, word pieces usually would be fall into a feature vector or feature space of a size 1K to 10K at most for English. If it's for the Mandarin, Mandarin use or Chinese, Chinese Mandarin is a speech. If it's for Chinese, we don't use word piece. We use something called character. And it's like a be like a E, R, or this means sun. And this word piece size is even smaller. And usually it's just less than 10,000 for Chinese. But let's see the case for speech. Take the mono-channel speech recognition, for example. Usually, the sampling rate is 16 kilohertz. What does it mean? This is sampling rate. And it's 16-bit quantized. The PCM quantization, okay? Which means for every seconds, you have 16,000 samples coming in, and it's being recorded. And each sample would fall into the region between 32,768 to 32,767 range. It's going to be an integer number, okay? So you can see, even for this one, for every feature sample space, or even just for one sample's feature space, it's the size of 2 to the 16. It's huge, right? Or say it's 65K. Compared to English, it's already very large. And what else? The thing is, if you're just trying to model the speech on the sample scale, okay, usually a speech sentence with a range from 5 seconds to 20 seconds. Let's say on average it's 10 seconds, okay? So then how many samples are there? So this is 10 times 16,000 times 65,000. Wow, this is I think I'm gonna just try to do the scales. It's like a 20 times K. This is a median, and then this is a K. This is 1. And I think for every 10-second speech, you're gonna get 10,000 median possible samples in the feature space. But for the natural language processing, say a sentence of 100 word pieces. What's the feature space of this? Or how many possible features are there? So this is gonna be 100 times 10K at most. So this is gonna be a million. So if you versus this and this, you would say, oh, the feature space or the possible feature space of speech, if I model everything in samples, would be significantly or greatly larger than the feature space that is being needed for the NLP. So the speech people has to come up with another feature space, okay? And people say, okay, why don't you just use phones? Definitely no, right? Why? Because this is pre-training, it's untranscribed. You don't have any labeled or transcribed information about the speech. You can say, I can do, why don't I just do some recognition? Recognize the speech first. Recognition first. Then this won't be pre-training anymore. So because you want to do pre-training, right? And I think people have tried a lot to get some concept of tokens, token for speech, recent years after the BERT coming out. Token for speech. And one successful tryout was by Facebook or Meta guys. They got something called a VQ. Wave to back. Correct me if I'm wrong. I think that was back in 2019 or 2020. And this is probably, they're very smart. What they are doing was that I do have a paper reading on their subsequent work, which is a Wave 2 Back 2.0. In our YouTube channel, feel free to check the details of it, which was published a few days ago. And this paper was published in 2020, I think. It's 2021. Yeah. And later on, they got something even simpler. It's got Hubert. Hubert, I think it's also 2020. Correct me if I were wrong, okay? Especially for the Wave 2 Back, I can tell you that the smart thing they're doing is that, so given a raw speech, they do take the raw samples into the input, raw sample sequence. They want to train a encoder and they want to get embedding, right? What they were doing is that instead of just putting in the same raw sample sequence at the output, which you try to re-estimate with some type of a decoder, this I just explained. This is like a mission impossible, right? Do this. So what they were doing is that they developed something on the side loop, which take the encoder's intermediate output into something called a quantizer. Which means they can map the raw samples into another feature space, which has roughly the size of 1K to 10K codes. This is a code book. Okay, a code book of size about 10,000. And this, you can see that they're doing the analogy or similar things like the NLP people do. Once they map these things to the code books, and the task become to be, you can either try to see if you can recover the codes, right? Because you can just code those samples into code 1, code 2, called N, right? And like the same thing that people do in the NLP, you can mask certain part of the speech. Suppose this is a recording, you can mask certain part of it and see if you can recover these codes. But the Wave2Vec people didn't do this. I won't go into details. I think it makes sense because it's still very difficult to, or say, to recover those codes may not make perfect sense because definitely the codes are the results of your estimation. You don't want to estimate on your estimates. That's strange. What they were doing is that they defined a loss called the contrastive loss. Contrastive loss. In the loss, they compare the distance of the vector of the embed and the quantized vector, which they call target. Target, which is quantized. Quantized from the code book, right? They compare these two vectors. Embedded vector, actually they call this context vector. Let's call this C, okay? And the target vector, well, let's call it Q. So the contrastive loss is to calculate the inner product or the distance between the context vector and the target vector. And the F function means the loss. This is a general concept. And it works very well. Although you can see that there are two things that you want to pay attention to. The first thing is that in the speech pre-training or Wave2Vec 2.0 training, there's no decoder. Decoder is gone. So this is why in the Wave2Vec 2.0 or Wave2Vec, you didn't see people talking about the transformer anymore. So because there's no decoder. And the second thing is that the contrastive loss, let me use the CL here. And you can just try to minimize the contrastive loss, but definitely you can never minimize the contrastive loss down to almost zero. It is impossible. This is different than the supervised training, which is almost the case that lots of time you wanted to reduce the loss, and the smaller the better, but definitely in this contrastive loss scheme, you can see that you're trying to minimize the loss between your embedding with another estimated stuff. Getting this thing to zero, first thing is difficult, and the second thing is that you may not want to get this to zero. Even you could, because that would suggest that your model might be overfitted to some certain local optima. Okay, that's my own understanding. All right, and the last or final thing I want to give you first quick introduce is that the size of the BERT, model size. I think BERT is one of the first model that come up with a super large size model, because I think according to their paper, they have a encoder model. It has a size of 300 million parameters. And then later on, I think what I know is that Facebook has a Megatron, right? Megatron. I checked a few days later. Megatron LM, which is also a pre-trained model, it has a size of 11 billion parameters. And I think you all know the GPT-3, right? GPT-3 is also a variant of the BERT model. It comes from the BERT model. Correct me if I were wrong, I think it's about 100 billion parameters. And I think lately, Huawei is getting another model they call the Alpha, or something called Pangu Alpha. I think this is even bigger than the GPT-3, but definitely bigger than the GPT-3. But I definitely forgot the size of it. And you may ask, Wei, what's the purpose of having such huge model? Let me tell you, my understanding is that the BERT and its variants or derivatives give the human being a chance to encode or compress almost all the knowledge that human being is having into one single model. You may say, okay, this 100 billion parameter model is big. But I would say it's not as big as you think, because definitely in the internet or the library, there are lots of texts. The text, if you look at all the texts that human beings are having or getting every day, it's definitely way bigger than the size of 100 billion bits or bytes. And this is a huge improvement, going from this type of unorganized, unstructured information into a organized, structured model or embedding generation model. So in this model, definitely for NLP, the biggest advantage of it, I think, or the advantage of it is that it can just incorporate the correlation between the words. Any two words you can think of, or any two sentences you can think of, what's the correlation between two sentences and the two paragraphs and the words between paragraphs, all the things you can name it, have those underlying information models. And then when people shift to the downstream tasks, like the QA task, NER tasks, people don't need that many transcribed information. No longer need that many transcriptions. Because transcriptions take human effort and time consuming, and definitely we human beings are not going to be capable of transcribing everything or everything in the text we have right now. And this type of pre-training then fine-tuning workflow has been demonstrated by the BERT people, saying that this is super effective in boosting the current state of our systems, accuracy, performance, F1 scores, etc., with a limited amount of transcribed data. Let's talk about speech to conclude. Definitely for the speech thing, you can see that this is also similar to the NLP case. There are lots of archived speech which exists on the internet. For example, YouTube, audiobooks. Lots of them are untranscribed. how do you leverage all these things and get a pre-trained model and use the pre-trained model for the downstreaming tasks, which has a limited amount of annotation, especially things like ASR. I think recently people got interested in something called meeting notes, which means you just listen to the people having meeting and get who spoke when, and for each speaker what he spoke, and then for the stuff he spoke, what's the emotion of his speech, and what's the semantic or structural information of it embedded in that speech. This type of analysis thing. All these things are called, these are supervised training, right? And you can see, especially for the ASR, especially for the meeting notes, it's hard to annotate those recordings with the meta information, the detailed information. But people are hoping that with the help of the pre-trained model, for instance, the Wake2Back or Hilbert or something else, people are going to be able to need less amount of transcribed data to perform the subsequent or downstreaming speech recognition tasks. Okay, today I'm going to stop here. I wish you enjoyed the paper reading of the BERT. Bye.